Welcome back. In this video, I wanted to cover some more difficult examples on how to set up integrals using different coordinate systems. So in this one, we have 4 different examples we're going to look at here. I've got these different domains and then each of the different integral problems that go with them. And we are going to decide which is the best coordinate system to express these in, either Cartesian, polar, cylindrical, or spherical. And then we're going to rewrite the integral in the respective coordinate system after we figure out how to make that kind of conversion. So let's go ahead and get started. So in our first example, we have that omega is equal to the points x, y, z in the first octant, such that x plus y plus z is less than or equal to 6. And we're going to find, or at least set up, the triple integral over omega of z squared dv. So let's go ahead and sketch a picture of the region so we can make our decision about what is the best coordinate system to use for this. So we're looking at x plus y plus z less than or equal to 6. Well, if that were an equal sign, this would be a plane. So we're kind of looking at the area bounded by the plane in the first octant. So that's going to be this region here. So x, the corner on the x-axis, has to be it has to be at 6. Similarly for y and z in this case. So we're looking at this particular region right here. Just like so. Okay, so let's kind of talk about what this looks like a little bit. This has a lot of corners and it's very flat along each side. And if we remember back to the video that I posted earlier about, kind of like the shapes of the spaces that we're working with, either, the rectangular coordinates or the polar, cylindrical, and spherical coordinates, that can kind of inform us what types of regions are best represented in each coordinate system. So we note that this has flat faces, like entirely flat faces, and lots of corners. So this means that we're probably going to want to use Cartesian coordinates. Well, in this case, it's actually already written in Cartesian coordinates, so we're just going to leave it as is. All right. That one was pretty simple. Okay, let's do another one. I'm going to need a new piece of paper for this next one, though. So our next example, we have that omega is equal to the set of x, y, z, such that the negative square root of x squared plus y squared is less than or equal to z, and y has to be greater than or equal to 0. And we have x squared plus y squared plus z squared is less than or equal to 16. And we're going to re-express the triple integral over this region of x dv. Okay, so let's draw this region. See what it looks like. I'm going to start by sketching that sphere, and then we'll fill in the rest of the information on it. So my sphere has radius 4 is what that tells me right there. This part a little longer. Okay. Label my axes. So 4, 4, 4, 4. I guess those are all negative, and then -4 down here. Okay, so then my sphere could look something kind of like this. Get some depth. Okay, there's a sphere, albeit a little bit lopsided, but that's a sphere. Now, so that takes care of this part. we want to take a look at something that has to do with this. Well, this right here is going to be an upside down cone is kind of the idea behind that shape. So you can kind of draw that right in here. Looks something kind of like that where it intersects our sphere. And we also know that we want y to be greater than or equal to 0. So first of all, the fact that y is greater than or equal to 0 tells us that we are dealing with kind of like the back half of this. So we're really just wanting this portion right in here. And then it can go up and over like so. But we also have to decide what to do with this cone part. Do we want the inside or the outside of the cone? So since we want negative of the square root of x squared plus y squared to be less than or equal to z, well, we notice that any positive value for z can fill this, okay? And there's really only two pieces in this region, right? We have the sphere outside of the cone and the sphere inside the cone. And positive values for z fulfill this very easily because any positive value for z has to be greater than or equal to any negative value that this is going to take. So that means that we're really probably going to be looking at the outside part of the sphere since that's what includes positive values for z. So in particular, we're looking at kind of like this part right in here and just like half of that outside of the cone, okay? So we're looking to exclude the cone and only have half of the sphere. So I guess it kind of looks like, I don't know, it's just like a circle with a hemisphere with a divot out of the middle of it. Or, I mean, I guess the way that I thought of it was a sphere minus the ice cream cone that pops up a lot in these types of problems. But anyway, because we're looking at this sphere minus this ice cream cone piece, or at least half a sphere minus the ice cream cone piece, we're really probably going to want to think about using spherical coordinates, okay? I don't know, whatever we called that piece there. And I should probably say it's like half a sphere. But being half a sphere versus all of a sphere really doesn't make a difference in whether we're going to use spherical coordinates or not. So. All right, so now that we've decided that we want to use spherical coordinates, we know that we want to re-express omega as being equal to something in terms of rho, theta, and phi. And we just have to come up with the restrictions for each of those. Rho is actually really quite easy because we can look back up to here and say, okay, this guy right here is rho squared. So we're going to need 0 less than or equal to rho less than or equal to 4 in this case. Theta is another one that should be at least, you know, somewhat straightforward because we can look at our XY plane, assign our values like we do on the unit circle. And say, okay, we only want the part that has y being positive. So that's just going to be the back half of this sphere. So that starts at 0, goes around, and then stops at pi. Those are all the values that theta can be. Figuring out phi, on the other hand, is a little bit trickier. The first thing we do is we notice that we kind of recall that pointing straight up, if rho is pointed straight up, this corresponds to phi equal to 0. Pointing straight down corresponds to phi equal to pi, and then phi is allowed to range anywhere in between. In particular, we're allowing phi to start here on our z-axis, and we want it to swoop down like this, pass through the xy plane, and then come down to right here. Okay, because we don't want it to go into this part where we took out the ice cream cone shaped piece. So we want it to stop right here. And if we remember from a previous video, this ice cream cone shape always creates pi over 4 type angles. So the angle between here, the negative part of z and pi, or z and this thing right here, this leg right here, that angle has to be pi over 4. So we're taking pi and subtracting off pi over 4 to figure out what this leg right here has to be. That must be 3 pi over 4 in this case. So we're starting at 0 and we're allowing it to swing all the way down to 3 pi over 4, but then it can't go any farther in because if we did, then it would start to include this again, ice cream cone shaped piece that we've removed from our sphere, and we don't want that. So phi can be anything that is sitting in this range right here. All right, so that's pretty much it. Now all we got to do, we've got our bounds. We just have to convert the inside of here and our differential. And the inside piece here, we can just use our identities, which tell us that x is equal to rho sine of phi, and then cosine of theta, and then dv is equal to rho squared sine phi cosine. Oops, not cosine. D rho d theta d phi. And again, the order of this really just depends on how we set up our bounds here. Since none of our bounds are dependent on each other, we can just order those however we want. So what we are going to get for our triple integral over omega of x dv, well, we still have a triple integral. X is going to become rho sine of phi cosine theta, and then we have rho squared sine of phi, and then d rho d theta d phi. And now that we have these guys lined up, I can fill in my bounds. So rho is going to go from 0 to 4, theta goes from 0 to pi, and then phi goes from 0 to 3 pi over 4. And that's pretty much all there is to that. We just have to set up the integral. We're not really asked to do anything else in this case, so don't evaluate that or worry about how that computes or anything like that. That's pretty much all there is to this problem. So again, the biggest hurdle is really just figuring out how to change your domain or your region so that way you can set up your new bounds of integration. Next problem, we have omega equal to the set of points x, y, z, such that 0 is less than or equal to z less than or equal to 2. And then we have x squared plus y squared plus z squared less than or equal to 16. And the interval that we're wanting to look at is the triple integral over omega of z dv. Okay, so as always, we're going to start by sketching our region. Again, I like to kind of start by drawing the sphere if I can, just because I think that kind of gives some nice bounds for the shape. So in this particular instance, again, we're looking at a sphere of radius 4. I'm only going to draw the top half because I'm told that z has to be greater than or equal to 0. So that's going to look something kind of like this, with the dome over the top like so. Okay, and then since z has to be less than or equal to 2, if we say right here is 2, that's going to kind of slice the top part of our sphere off. Okay, so the piece that we're really interested in then is going to be this kind of like weird I mean, like, it's a sphere that's been cut in half and then we cut off the little top of it. And specifically, a little top got cut off at where z is equal to 2. So, well, we have to decide what kind of coordinate system we want to be able to use for this. And it's going to be really tempting to say, okay, this looks like part of a sphere, so therefore we are going to use a sphere. Or it may be even more tempting to continue with that line of logic and be like, we have z squared right here. If we have z squared, we want to use spherical coordinates. That's a nice guideline, but it's not always true. And I mean, like I mentioned that in my in a previous video that, you know, you can kind of look at it and be like, okay, z squared, maybe you want to use spherical coordinates. But again, it's not always true. Looks like it's part of a sphere. Do we want to use a sphere? No. Another way to view this particular shape, and I can draw this separate from the coordinate axes and maybe make it a little bit more clearer what it looks like. It's something kind of like this. And the way that I chose to think about it, it's kind of like a plump cylinder, okay? You got this little like the cylinder shape on the inside here, although it's solid on the inside, and it's a little bit extra round on the outside of it. A little bit squished. And so since it's actually its basic shape, if we ignore the fact that it came from a sphere, its basic shape is actually a lot more like a cylinder. And so because of that, I think it makes a little bit more sense to approach this using cylindrical coordinates. And in fact, if you try to do this with spherical coordinates, you're going to wind up having to chop up your region, and it does not work out very nicely at all. So we're going to go for cylindrical coordinates, which means that we want omega to ultimately be in the form of r, theta, and z. And another maybe hint that you'd want to use cylindrical coordinates instead of spherical coordinates is that we have a restriction solely on z. And anytime that you have a restriction solely on z, sometimes it can be a little bit tricky to work that into spherical coordinates. You can try it, and sometimes it shakes out really nicely. We've had examples in the past where that's been the case. But a lot of times when you see just z by itself having a restriction on it, you're going to want to be looking at using cylindrical coordinates, because cylindrical coordinates allow for z to just do whatever it wants. Okay, so let's go ahead and start making these restrictions here. So, well, I mean, the obvious one is that z is between 0 and 2. I mean, that's given to us, right? And so I guess I can write that information down. And then maybe the next easiest one here is going to be working with theta. So theta starts at 0, pi over 2, pi, 3 pi over 2. And we want it to go all the way around and create this circular shape. So theta has to go clear around like this. Whoop, just like that. So theta can be between 0 and 2 pi. Because that's what gives us the full circle. Now, the tricky part becomes, what do we want to do with r? Well, we still have one more piece of information that we haven't used. It's that x squared plus y squared plus z squared is less than or equal to 16. So this piece right here can become r squared. So we have r squared plus z squared is less than or equal to 16. And since cylindrical coordinates allow z to be, part of the coordinate system, it's okay to have z right here. That's totally fine. We don't have to worry about eliminating z. And what we're going to get is that r has to be less than or equal to the square root of 16 minus z squared. And basically what that does is it allows it just kind of like allows the radius to change kind of here on the inside depending on how tall z is. And so that is what's going to account for our kind of domed shape that we have here on our sides. So we have that, well, and then of course it's greater than or equal to 0. So 0 is less than or equal to r, less than or equal to the square root of 16 minus z squared. And then we have theta, which is between 0 and 2 pi. And then I have z being between 0 and 2. Oops, z. Great. Okay, so now I just have to set up my integral. So we started with a triple integral over omega of z dv. And we have triple integral. Z gets to stay the same because, well, z is just z when we're working with cylindrical coordinates. And dv becomes r dr d theta dz. And in this particular instance, the order of these is actually really important because we have bounds on r that are dependent on z. So we need to make sure that dr makes an appearance before dz. Now, theta versus z, that doesn't really matter because these are both numbers on here. But again, because the bound of r is going to have z inside of it, we have to integrate with respect to r before we can integrate with respect to z. So our bounds on r are 0 to square root of 16 minus z squared. For theta, it's going to be from 0 to 2 pi. And then for z, it's going to be from 0 to 2. And that's pretty much all there is to that problem. Again, this one was a little bit tricky because it looked like maybe it belonged in spherical coordinates, but in reality, if we kind of ignore where it came from and say, well, this is the basic shape of the thing, it looks like a squished cylinder. Cylindrical coordinates are a much more reasonable choice, especially since we have this dependence for z here that is just, it's only in terms of z. There's no other part of the equation involved in that. So. All right, one last example. In this one, we have omega equal to xyz such that z is greater than or equal to 0, x is greater than or equal to 0, and then I've got x squared plus y squared is less than or equal to 4, and then we're going to have z be less than or equal to 8 plus 2x plus y. Okay, and and we're doing a triple integral over omega of z dv once again. Okay, so for this one, let's go ahead and sketch our region. This right here tells me it's a cylinder. This right here tells me that I'm on the positive part for z. And then this is going to tell me that I want the positive half for x, but I'll draw that in later. So notice that there's no z squared in here. That's why I know it's a cylinder and not a sphere. Since it's not dependent on z in any way, the height of it isn't going to be limited. So it's just always a circle of radius 4 going upward toward infinity, because z can be whatever it wants. Okay. So here's kind of our shape. Like so. I think I'm going to need a little bit bigger coordinate axes here, because I also still have to include our plane. Okay, so now we're going to draw, well, the plane. And the plane here is z less than or equal to 8 plus 2x plus y. So since z is less than or equal to 8 plus 2x plus y, I know that the height of this thing has to be at least 2. Call that 8. Rearranging this a little bit, and we're going to get that 2x has to be, well, x basically has to be less than or equal to -4. So that's going to put it right here. Kind of like right down there at the base. And then I'm going to have that y also has to be less, or greater than 8. So we're going to be looking at, or greater than -8, sorry. That's going to be really kind of more like out here. Oops. So I extended my lines in the wrong direction. All right, here we go. Our plane is going to look something kind of like, I'm not very good at drawing these things, to be honest. Like so. Okay, our plane's going to slice through like that. And so the region that we're really going to be interested in here today, since we also want x to be greater than or equal to 0, is going to be this piece here. And then maybe up toward this way, swooping around this direction a little bit, and then it's going to kind of slice there. I'm going to put some kind of like slices in here, and then like that. It's a little bit tough to see what this looks like, but that continues onward towards infinity. Basically, it's a cylinder that you've kind of sliced a side off of, and then we cut it in half further by taking x to be greater than or equal to 0. The main point of this is a portion of a cylinder. All we've done is just sliced a few pieces of the cylinder off at straight lines, okay? And as a result, since we still have this kind of basic shape of the cylinder, you know, the curved sides with the flat top and bottom, we're still going to have a cylinder, and we're going to want to use cylindrical coordinates. So I think of it as a cylinder with kind of like a slanted top, but again, round sides, flat top and bottom. And we're going to want to use cylindrical coordinates. So D is going to be equal to R theta Z, and we just need to come up with expressions for each of these. Okay, so once again, R is going to be kind of, well, I mean, okay, I guess R wasn't really the easy one in the last one, but a lot of times R is going to wind up being the easy one, because we know that we have the x squared plus y squared less than or equal to 4. So we're going to have R squared less than or equal to 4, which means that R has to be between 0 and 2. Okay, and then theta is also going to be relatively straightforward, again, because So that's 0 degrees, pi over 2 degrees, pi degrees, and then pi over 2 degrees, or negative pi over 2 degrees over here. And we want theta to start here and just only go halfway around. So we need theta to be between negative pi over 2 and pi over 2. And then finally, Z is kind of the tricky part, right? Because that's the up and down. And it was kind of the top part of this cylinder that's a little bit messed up. So, well, we have this expression for Z right here. So, I mean, like, maybe the immediate thing to do would be to go in and we're just going to substitute out for our identities. Never be afraid to just kind of plug some things in and see what happens. So we're going to get Z is less than or equal to 8 plus 2r cosine theta, and then plus r sine theta. And we can actually just go ahead and say that this is our boundary right here. We don't really have to do any other rearranging. The only thing is that we would have to take care with our order of integration to make sure that we integrate with respect to r and theta after we integrate with respect to Z. So Z is, oh, and we're also told that Z is greater than or equal to 0. Okay, well, that's our bounds of integration. And converting this over is really, again, quite easy because Z is left alone and dV is RD. This time we're going to want to use Z first, dr d theta. The dr and d theta don't matter too much, just so long as Z comes before both of them. So our integral over omega of Z dV is going to be equal to triple integral Z, and then R, and then we got to make sure to do dz first because the bounds of Z are dependent on R and theta. Although these two don't matter what order they're in, just make sure that Z is first. So then we get 0 to 8 plus 2r cosine theta plus r sine theta. And then we get negative, nope, we're doing r next, 0 to 2, and then negative pi over 2 up to pi over 2. And that's it. Okay, so we've filled in all these pieces, and actually integrating this really isn't that bad. Unlike some of the other ones that we've looked at, I don't know necessarily how nicely those would shake out with integrating, but this one would integrate really quite well after you'd start with Z, and then you would get the r cosine theta and stuff like that, and it would all shake out really nicely. So yeah, that's pretty much it. Thank you so much for watching. Again, this video is kind of designed to accompany the video that I did earlier about the shapes in the coordinate system. So if you kind of watched this and didn't see the other one first, I recommend that you would go back and see that one again. So anyway, I'll see you guys next time.